Welcome to Lecture 6. In this lecture, we will solve some problems related to the concepts of vector spaces and bases. Let's jump right into this. We'll look at some problems from section 7.4, and the instructions for all these problems will be the same. The instructions are as follows. It says, is the given set of vectors a vector space? So that's the first question, and it says give reasons. And then after that, it says if your answer is yes, determine the dimension and find a basis. And then it also tells us V1, V2, ... denote components. So in other words, whenever you see the notation in these next few problems, whenever you see the notation V1, V2, you might be tempted to think that those are different vectors, but they're not. They are different components of a vector. So let's look first at problem 7.4.28. And it says all vectors in R3 with 3v2 plus v3 equals k. So let's make sure now we understand exactly what they're talking about. The typical vector in R3, if we're using V1 and V2, etc., to denote the components, then the typical vector in R3 would be V1, V2, V3. That's the typical vector in R3. And so in this problem, we are considering those vectors in R3 that satisfy this equation, 3v2 plus v3 is equal to k. So we're not considering all vectors in R3, we're only considering those that satisfy this equation. And the first question is the given set of vectors a vector space? So let me ask, is this a vector space? And two of the easiest things to check if you have a set of vectors and you want to determine whether or not they are a vector space, two of the easiest things to check right away will be what's called closure under scalar multiplication and closure under vector addition. Now, what does this mean? Closure under scalar multiplication. Okay. Now, how do we check to see if this set of vectors, in fact, let's back up. What does it mean to say that this set of vectors is closed under scalar multiplication? Well, what we're doing here is actually asking the following question. If V1, V2, V3 is an element of, now we have not given a name yet to this this set of vectors, so let me back up here and we'll just call it capital V. The problem doesn't state a name, but we can call it V. So if V1, V2, V3 is an arbitrary element in V, it's an arbitrary vector in V, and lambda is any scalar, then is it true that lambda times V1, V2, V3 is an element of V? If so, V is said to be closed under scalar multiplication. And of course, if not, then V is not closed under scalar multiplication. And the reason that we're interested in this idea is that any vector space must be closed under scalar multiplication and also closed under vector addition. Those will be the two properties that you should check to make sure of whether or not a certain set of vectors is a vector space. Those are really not the only two properties that a vector space has. You can look in your book for the other properties, but in general, the other properties will be satisfied. But those two properties that I just mentioned, closure under scalar multiplication and closure under vector addition, those are the two that you will need to check. So, so we're first checking closure under scalar multiplication. Now, and we said that amounts to asking this question right here. If V1, V2, V3 is any element of V, and if lambda is any scalar, then is it true that lambda V1, V2, V3 is in V? Well, let's try to figure out the answer to that. Okay? Well, lambda times V1, V2, V3 will be equal to lambda V1, lambda V2, lambda V3. And we want to know, is this in V? Well, remember that the way that you check to see whether or not a vector is in V is you take 3 times the second component of the vector and add that to the third component of the vector and see if the sum is equal to k. So that's what we will do here. We'll say this is equivalent to asking is 3 times lambda V2. That's 3 times the second component. Remember, we'll come up here. 3 times the second component plus the third component. The third component is lambda V3. Is that equal to k? Well, how do we answer that question? Well, let's do it like this. We'll say 3 times lambda V2 plus lambda V3 equals question mark k. And the question mark means we don't know if it's equal to k. We're asking that question. Well, if we multiply out the terms on the left-hand side, we get 3 lambda v2 plus lambda v3 equals question mark k. And now if we factor out lambda on the left-hand side, this is the same as lambda times 3v2 plus v3. And we want to know if that is equal to k. Now, since we're assuming that v1, v2, v3 is in v, and remember up here, v is the set of all vectors such that 3v2 plus v3 is equal to k, then when we come down here, and this 3v2 plus v3 must be equal to k. So we have, is lambda times k equal to k? Now remember, lambda can be any scalar. And for scalars, we're typically going to be considering either real numbers or complex numbers. So can we say that for any real number, lambda k is equal to k? Well, the answer is, of course, no. Because, for instance, if let's suppose that lambda is equal to maybe 7. Is 7k equal to k? Well, no, unless k equals 0. So V is not a vector space unless k equals 0. And actually, if we checked closure under vector addition, we would come to that very same conclusion. We really don't need to go any further here unless you want to assume that k is 0, but let's just see how it would go. So closure under vector addition, how would we check that? Okay, well here you pick 2 vectors in V. So we'll say let v11, v12, v13, and v21, v22, v23 be elements of V is v11, v12, v13 plus v21, v22, v23 an element of V? If so, V is said to be closed under vector addition. If not, then V is not closed under vector addition. And as we've already said, this is one of the key properties of a vector space. So let's see what happens, okay? v11, v12, v13 plus v21, v22, v23. If we add these together, we get a vector whose first component is v11 plus v21. The second component will be v21 plus, v12. v12 plus v22. And the third component will be v13 plus v23. And we want to know, is that is this in V? Well, that's the same as asking if 3 times the second component plus the third component is equal to k. So we say 3 times V12 plus V22 plus, that's 3 times the second component plus the third component, V13 plus V23, equals question mark, is that equal to k? If 3 times the second component plus the third component is equal to k, then this vector is in V. But if it's not equal to k, then it's not in V. Okay, well, let's see what happens. If we multiply this out on the left-hand side, we get 3V12 plus 3V22 plus V13 plus V23 equals question mark k. And now let's regroup, and we can write this as 3V12 plus V13 plus 3V22 plus V23 equals question mark k. And now notice that this first parentheses, the terms there, 3V12 plus V13, that's 3 times the second component plus the third component of this first vector. And this first vector is in V, and therefore 3V12 plus V13 is equal to k. So we have k. And likewise, 3V22 plus V23, that's 3 times the second component plus 1 times the third component of this second vector, which is also assumed to be in V. And therefore 3V22 plus V23 is also equal to k. And so we have, is k plus k equal to k, which of course is the same thing as saying, is 2k equal to k? And again, our answer is no, unless k equals 0. Now, I want to repeat that, since we already found out that the closure under scalar multiplication is not satisfied unless k is equal to 0, we really could have stopped there, and just that could have been our answer, is that this is not a vector space unless we assume k is equal to 0. But I wanted to show you also how you check closure under vector addition. And interestingly, when we checked this for closure under vector addition, we came up with the same conclusion there, that again, this is not closed under vector addition unless k is equal to 0. But in both cases, if k is equal to 0, then the property is satisfied. In other words, if k equals 0, the set V will be closed under both scalar multiplication and vector addition. In this case, V would indeed be a vector space. But if k is non-zero, V is not a vector space. So that is how you would answer the first part of this problem for this particular case, is that this set of vectors, the set of all vectors in R3 with 3v2 plus v3 is equal to k, that is not a vector space unless k is equal to 0. So let's, just so that we can see how the rest of this problem would go, let's say, so for the rest of the problem, assume k is equal to 0. So then V is a vector space, and the rest of the problem then, in the case when it is a vector space, remember, if your answer is yes, then we want to determine the dimension and find a basis. So we now want to find, actually, well, I'll go ahead and say find the dimension and a basis. Okay, so how would we do this? Dimension. Okay, we're looking at the set of all vectors in R3. And of course the dimension of R3 is 3. So the underlying set here has a dimension of 3, but we're not going to consider all the vectors in R3. We are only interested in those vectors that satisfy the condition 3v2 plus v3 is equal to k, which now is 0. Because remember, we're only considering this case k is equal to 0 because if k is anything other than 0, this isn't even a vector space, and therefore it wouldn't make any sense to talk about the dimension or finding a basis. So we're only interested in those vectors in R3 that satisfy 3v2 plus v3 is equal to 0. Now the underlying space R3 has a dimension of 3, and we are placing one restriction on it, so the dimension of V is equal to 3, which is the dimension of the underlying space, minus 1, which is the number of restraints, and so the dimension is going to be 2. And now the only other thing that we need to do, we need to find a basis, and a basis will just be a linearly independent set of vectors that satisfy this equation, 3v2 plus v3 is equal to 0. And how many vectors are we looking for? Well, remember that the number of vectors in the basis for a vector space is equal to the dimension. So we're looking for two linearly independent vectors that satisfy 3v2 plus v3 is equal to 0. And this is very easy to find. For instance, one possibility would be 1, 0, 0. Because 0, if v2 is equal to 0 and v3 is equal to 0, then certainly 3v2 plus v3 is equal to 0. And now we need to find one more vector that satisfies this, and I would choose 0, 1, negative 3. That's a very easy choice. Now, why did I choose 0? Well, by choosing 0, you make sure if the first vector has 1 as the first component, and the second one has 0 as the second component, 0 as the first component, then there's no way these two vectors could be multiples of each other. So automatically, this will make sure that these are linearly independent. If you have two vectors, they will definitely be linearly independent as long as one isn't a multiple of the other, or the 0 vector. So that's the reason of picking 0 for the first component. You don't have to in this case, but it's convenient. And then as far as the other two components, well, I picked 1 because that's an easy number to deal with, But if I pick v2 is equal to 1, then the only way I can then make this equation true, 3v2 plus v3 is equal to 0, would be to choose v3 is equal to negative 3. So this is a possible choice for the basis in that case. It's not the only possible choice, but it is a choice, and that is the way that we would solve problem 7.4.28. Now I know that was a lot to digest, so but I think if we do another problem or two like this, it'll become a lot clearer. So now let's look at problem 7.4.30. And this one, at this time, v is going to be equal to the set of all vectors in Rn with the first n minus 2 components 0. And so again, we want to know, is this a vector space? And then if the answer is no, we're done. But if the answer is yes, then we want to find the dimension and a basis. So is this a vector space? And the way we check that again is we check for closure under scalar multiplication and vector addition. Okay, closure under scalar multiplication. Let v1, v2, vn be a vector in V, and lambda is any scalar. And then we ask, is lambda times v1, v2, vn an element of V? Okay, well, lambda v1, v2, vn is equal to lambda v1, lambda v2, lambda vn. And we're asking, is this an element? So I'll put a question mark over that sign. Is this an element of V? Well, remember, that's equivalent to asking if the first n minus 2 components are equal to 0. If the first n minus 2 components are equal to 0, then this is an element of V. If not, then it's not an element of V. Well, remember that we started off here with a vector that is in V. So that means V1 and V2 and V3 all the way up to Vn minus 2, all of those are 0. So if the first n minus 2 components of this vector are 0, then when we multiply them by lambda, then the resulting vector here will also have its first n minus 2 components equal to 0. So the answer in this case is yes. So V is indeed closed under scalar multiplication. In other words, when we take any vector of V and we multiply it by a scalar, we still get a vector in V. Okay, now we need to check for closure under vector addition. V needs to have both of these properties in order to be a vector space. And you probably already know the answer. Just think, if we if we take two vectors in V and add them together, will the sum vector be in V? Well, remember, the way that you check that is to look at the sum vector and check its first n minus 2 components, and you ask, are the first n minus 2 components equal to 0? If so, then the vector is in V. If not, it's not in V. Well, those first n minus 2 components are formed from the first n minus 2 components of the two individual vectors, and both of those have the property. Well, maybe I should just spell this out. So let's let v11, v12, dot, 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 v1n. So we'll say let that vector and v21, v22, dot, 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 v2n. These will be two elements of V, and what we're asking here is v11, v12, dot, 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 v1n plus v21, v22, dot, 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 v2n. Is that an element of V? Well, v11, v12, dot, 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 v1n plus v21, v22, dot, 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 v2n, that is equal to the vector whose components are v11 plus v21, v12 plus v22, dot, 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 v1n plus v2n. And we want to know, is that in V? Which is equivalent to asking if these first n minus 2 components are 0. But remember, since these two individual vectors are both in V, then the first n minus 2 vectors, the first n minus 2 components of this vector is 0, and the first n minus 2 components of this vector are 0, and so when we add them, the first n minus 2 components of the sum vector will indeed be 0, and so therefore the answer is yes. So V is also closed under vector addition, and V is indeed a vector space. And so now we want to, as we did before, find the dimension and a basis. Well, the underlying space here is Rn, and the dimension of that is n. Now, how many restraints are we imposing? Well, we're imposing the constraints that each of the first n minus 2 components is equal to 0. So that's V1 is equal to 0, V2 is equal to 0, V3 is equal to 0, all the way up to Vn minus 2 is equal to 0. And so therefore we have n minus 2 constraints on this, and so the dimension of V is equal to the dimension of the underlying space, which is n, minus the number of constraints, which is n minus 2, and therefore the dimension in this case is equal to 2. And what is a basis? Well, a very easy basis for this problem would be the following. Okay, let's look at these two vectors. Notice that the first n minus 2 components of this vector are all 0, and the first n minus 2 components of this vector are all 0. So both of these vectors are definitely in the set. And what we've done here is for this first one, we have made component number n minus 1 equal to 1. And in the last one, component n is equal to 1. That assures that these two vectors are linearly independent, and these two vectors are both in the vector space, and therefore this is a very easy basis for the vector space under consideration in this problem. So that's how we would do 7.4.30. Let's do one last problem of this type, and I think that it will make everything clear. And, well, let's just see how it goes. So in problem 7.4.34, V is equal to all vectors in R3 with 3v1 minus v3 equals 0, and 2v1 plus 3v2 minus 4v3 equals 0. Okay, so the first question is V a vector space? And as usual, what we want to do is test for closure under scalar multiplication and vector addition. So, as usual, we will let V1, V2, V3 be an element of V, and lambda is any scalar is lambda times V1, V2, V3 in V. That's the question for closure under scalar multiplication. So let's see how this goes. Lambda times V1, V2, V3 is equal to lambda V1, lambda V2, lambda V3. And we want to know if that is in V. Well, the way that you check to see if a vector is in V is you need to check two constraints here. Is 3 times the first component minus the third component equal to 0, and is twice the first component plus 3 times the second component minus 4 times the third component equal to 0. So you have to check two conditions. Okay, so we have 3 times the first component. That's 3 times lambda V1 minus the third component, which is lambda V3. Is that equal to 0? And we also have is 2 times the first component, is lambda V1, plus 3 times the second component, minus 4 times the third component, is that equal to 0? Okay, so let's check these two conditions. Well, we can rewrite this first equation like this. And the second one can be rewritten like this. Now, remember that this vector we started with, v1, v2, v3, is assumed to be in V. And therefore, if it's in V, then it satisfies both of these conditions. So that means that 3v1 minus v3 is equal to 0, and 2v1 plus 3v2 minus 4v3 is 0. So our two equations now become this. And of course, this second one should be 0 here. And of course, the answer to both of those is yes. So V is indeed closed under scalar multiplication. And I'll leave it to you. You should verify, as we have done above, that V is also closed under vector addition. So V is a vector space. And now, as usual, we want to find the dimension and a basis. Dimension, okay, the underlying space is R3. So we have 3 minus the number of constraints. The number of constraints here is 2. We have two equations that must be satisfied. So 3 minus 2 is equal to 1. The dimension of V is equal to 1. And therefore, the basis will consist of only one vector. We need to find one vector, one non-zero vector that is in V, and that will be acceptable as a basis for V. Okay, now the easiest way to do this is just look, we need to satisfy both of these equations, and so what I would do if I were you is to say, okay, we can pick, to satisfy this first equation, we could pick V1 is equal to 1 and V3 is equal to 3. Then the first equation will definitely be satisfied. So V1 is 1 and V3 is 3. Now we need to figure out what V2 would have to be to make the second equation also satisfied. Now remember, we have V1 is equal to 1 and V3 is equal to 3, and so therefore this equation would become 2 plus 3V2 minus 4 times 3 is minus 12 is equal to 0, and therefore we have 3V2 is equal to 10, and V2 is 10 thirds. So we can come down here and say 10 thirds. And this is a vector that satisfies both of the constraint equations, and it would be an acceptable basis for V. So that's how we would do problems of this type. And now let's look at some problems for this lecture. So now we'll look at some problems for this lecture, but first I want to correct a very minor error that occurred in the lecture. On this last example that we did, I stated that that was problem 7.4.32 from the text, but instead that was actually problem 7.4.33. So just that minor change. Okay, so now we'll go and look at the problems for this lecture. Problem 6.1. For the set described in problem 7.4.27, so you'll need to look in your book and see what that is. But for the set described there in that problem, circle all that are true. A, this is not a vector space. B, this is a vector space of dimension 3. C, a basis for this vector space is the set consisting of the three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Or D, a basis for this vector space is the set consisting of the vectors 1, 1, 0, and 0, 2, 1. So that's problem 6.1. Just circle all of those that are true. And then for problem 6.2, it's very similar. It says for the set described in problem 7.4.29, circle all that are true. Choice A, this is not a vector space. Choice B, this is a vector space of dimension 3. Choice 3, a basis for this vector space is the set consisting of the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Or D, a basis for this vector space is the set consisting of the vectors 1, 0, 0, and 2, 1, 1. So that's the those are the two problems, the in-lecture problems, and then we will have another problem about this on the quiz, and it will be similar in nature to these two. So that concludes lecture 6, and good luck.